Hi, thanks for tuning in. This is Ben Glocker from Imperial College London, and today I'm going to talk about some aspects around the training data that we want to use for machine learning. So let me start with quickly some disclosures. So I work with these companies. However, this is unrelated to the following talk. So I want to start with a quote by Professor Neil Lawrence: "Data everywhere, not a set to process," which is often a situation we find ourselves in the context of using machine learning for medical imaging. And I first want to talk about some aspects about what does it make to have good or bad data available. So the first aspect is data quality. Everyone working with medical imaging will have realized that sometimes these images can have issues. There can be artifacts, there can be noise, there can be corruption in the data. And data quality then actually impacts machine learning heavily, because we need to consider whether we want to be robust to this or whether we want to do a analysis quality control, or whether we want to filter out those images. So this is something we need to consider. Is the data quality something that we want to automate to check for, or whether we want to maybe have a human in the loop that does some quality control on our data? So 2 years ago at ECR, I already talked about an aspect of data variety, which still is a major issue and major challenge to overcome in machine learning. However, it has been recognized, I think, more over the last years in the community. And the issue is around the variety that we are willing to accept, both at training time and at test time. So if we are training a machine learning model on something like on the left, where everything's clean and homogeneous and well curated, such a model might not work very well or at all on test data that is very heterogeneous, like on the right-hand side. So we need to make a decision whether we want our model to be able to work with heterogeneous data. And that means probably that we already need to take this into account when building our training data set. Or do we want a more narrow scope solution that maybe only works in cases where we have a relatively clean and homogeneous data environment? So now this has been recognized. If you actually submit a machine learning method to a clinical journal, they would expect you to show that you have, for instance, done an external validation to show that your model works on new and heterogeneous data. So data volume is another aspect. How much data do we need for machine learning? The typical question would come from the clinician, and the ML researcher might say, how much data do you have? Because obviously we would like to get started and use as much data as possible. The issue is that classical statistical assessments do not always apply. We cannot just do a power calculation and know how much data we need. But the good news is machine learning has mechanisms to tell us whether more data can be helpful. So we need a starting point. So if we are brave enough and start our machine learning project, we can do an error analysis, for instance. We can check how well do we do on the training data, and also maybe on the internal test data. And what we do find, if we plot this against the training size, is that if we are still having a very large training error, or an unacceptable training error, even after increasing the training size, we are living in this regime of high bias. Our model doesn't explain well the data. So there's very little hope that even with more data, we can do better. So in this case, more data won't help, and we need to consider using a different machine learning model in the first place. However, if we're in the regime of high variance, where actually we explain our training data quite well, so we have an acceptable error on the training data, but there's still a gap to the test data, so we're not happy with the test performance. In this case, we might actually want to go out and collect more data, because it might help to close that gap. Maybe our training data so far hasn't captured the variety that we would expect it to cover. There's something called the data readiness, which is a very useful concept introduced by Neil Lawrence that might help us to communicate and discuss whether data is ready for machine learning. So initially, this discusses 3 bands. So there's a band C, is the data accessible? Maybe we just have a belief that some data may exist. That's often the start of a project. And then we need to check whether this data is faithfulness. So if it's available, is it actually also faithful? Is it correct? Is any data missing? What's the format? Can we actually use it? Now, this brings us to band A, which now talks about the appropriateness. Is the data available actually useful for the particular task we're trying to solve. And I believe a lot of machine learning projects might fail because they have reached band B, but at the end, maybe it turns out that the data wasn't appropriate for the task to solve. So it's important to have a mechanism to discuss data issues and data aspects. We try to do this by introducing the MEDA scale, which talks about 4 levels. So together with Hugh Harvey, we brought this data readiness levels to the context of machine learning for medical imaging. So you can have a look at this paper, which discusses this in more details. But the idea is really to have a way of communicating and discussing more transparently what we believe, what the state of the data is, and in which state we are, and where we might need to invest certain resources to get to the next level. So in the second part, I want to talk about a new idea about discussing the relationship between images and annotations. So just as a reminder, what we are trying to do is to build a predictive model, right? So we are trying to build a machine learning model that can, given an image X, predict the probability of a certain label Y, let's say a diagnosis. Now, we are making big assumptions here. The first one is that actually there's enough training data available, right? So this goes to the point of data volume. But the other aspect, important aspect, is that we're assuming that the training data and the test data come from the same distribution. This goes back to my example about the pumpkins, the illustration of the homogeneity in our data sets. Here we are typically assuming that this model works well if the training and test distribution are very similar, which might be violated in practice. So we wanted to understand a little bit more about the relationships between images. So we looked at this from a causal perspective. Who's causing who? So is the image causing the label, in which case we are in the causal relationship. We are predicting the effect from the cause when we build this model, right? But there might also be the anti-causal relationship where the label is causing the image. In this case, we are predicting the cause from the effect. Note that we're still looking at the same conditional distribution. Given an image, we want to know the probability for a certain label. So does it matter which relationships we have between our images and annotations? Let me first show you some examples to convince you that those two relationships exist in practice. So skin lesion classification, we have images X, demoscopic images. And let's say our labels are biopsy-derived diagnosis. So very close, probably the closest you can get to a ground truth diagnostic label. We would argue in this case we have an anti-causal relationship. The label, the disease is actually causing the image, right? So our causal diagram would look like this. The prediction, however, goes in the opposite direction. In brain tumor segmentation, it might be the other way. So we say our image X, maybe a structural brain MRI, and our label here is a manually drawn contour, let's say in radiotherapy, for instance. We would argue that this is a causal relationship. The image is causing the contour. An expert sits down and draws the contour on the image. The relationship is still disease causes image, but image causes the segmentation or a contour that we are trying to predict. So the prediction goes in the direction of causality. Now, it's not always that easy. Here's another example where we argue it can be quite tricky to establish the causal relationship. And this is an example that has been discussed quite a lot in the literature, taking radiology reports. So let's say our images are chest X-rays, and the diagnostic label is extracted from a report, let's say using natural language processing. So what is the causal relationship between the two? We argue it's not easy to establish because we're lacking some important information here. How is the diagnosis exactly derived at that is written down in the report? Is it derived from the image directly? Or maybe there were some additional tests, some lab tests, some other important tests, diagnostic tests that are maybe even more important than the image itself. So who's causing who here is a little bit tricky to answer if we're lacking some important meta information. So going back to the causality question, does it actually matter which direction we are looking at? So we argue in a recent paper that it matters a lot for key challenges in machine learning: data scarcity, data set shift, and sample selection bias. Let's just talk about two of them here: data set shift and selection. So in data set shift, what we now can do using causal diagrams, we can clearly communicate what type of a shift do we expect to happen. So here's a causal diagram again, image X and label Y. in the causal. So the first row is all about causal relationships. And we can use a domain indicator to say, where do we expect shifts to happen? Is it on the population, right? So the true unobserved physical reality of the patient that gets scanned, is this affected whether we are at the training time or at the test time, whether we are in hospital A or hospital B? So this might be population shift, or might cause population shift. This could be acquisition shift, where the image is affected, whether we are in hospital A or hospital B, using scanner A or scanner B. We could have an annotation shift. Depending on where we are, the annotation might change if people are not following a standard operating procedure, which is a really tricky one to solve for machine learning. In the anti-causal direction, we might have things like prevalence shift, right? The label prevalence might change. We could have manifestation shift or acquisition shift. So we're discussing these different shifts in more detail in the paper. However, it's good to realize that causal diagrams allow us to clearly communicate and make it more transparent what type of shifts we might expect. And they will have different problems, but also different mitigation strategies that are very important to consider when building machine learning models. Going back to the brain tumor segmentation example, we can now extend our causal diagram by making very clear that we might expect some population shift, for instance, right? The train or test domain or the development and deployment domain might have an effect on what type of, like the probability of diseases or ages that we might see. It might also be that the scanners change, so we might have an acquisition shift. So this arrow would indicate that we might expect an acquisition shift. So now going to dataset bias, which I think is one of the key problems that we currently face when doing machine learning. And this concerns sample selection biases that we introduced when actually starting to create our training datasets in the first place. You can do completely random, right? So you just take whatever you get. So here, this is independent of whether it's a causal or anti-causal relationship between the images and the labels. And this S is the selection variable. But if we, for instance, do it image dependent, let's say we screen our images by quality. We remove all the low quality scans or low resolution scans or scans with problem. We make it image dependent. If we do it based on the disease label, we make it target dependent. So we might select only certain diseases or certain types of patients and discard others, exclude others. So this would make our selection a target-dependent selection, or it could be based on both. And again, this has different results in terms of bias that we introduce, and it's really important to realize what type of bias are you baking into your machine learning model, because that will obviously affect your performance later at deployment stage. So going back to the skin lesion example, we can now very nicely illustrate in the causal diagram that we might have some bias introduced by producing the training dataset. Remember that we said our label is a biopsy-derived diagnosis. Now, when do we do biopsy? Maybe we only do it on images that were suspicious in the first place by visually looking at them. So that means our training dataset is already biased based on that the images looked suspicious. So probably this is not a screening population. So if we're training a model based on this data set, would we expect it to work in a screening environment? Probably not. So causality really matters, and it helps us to illustrate problems that might come down the road when using machine learning. It's very helpful to use causal diagrams, for instance, to illustrate potential biases, potential problems that we might face when building this model. It helps us also to be more transparent about our communication, about the findings, about the results. So this relates to guidelines and regulation. There's a lot of talk about how to best report machine learning studies, AI in medical imaging, and generally healthcare requires us to be transparent and to scrutinize the results. And we believe causality could help there and be one important aspect in the future. So if you're interested, there's much more detail in this work by Daniel and Ian and myself, where we talk and try to talk you through a little bit about the use cases of using causality in the context of machine learning for medical imaging. I also want to make a little bit of an advertisement. There will be a tutorial later this year at the MICAI conference. So if you're interested in how causality could be used, or you want to learn about the basics of causality in medical image computing, I invite you to join this tutorial in October. Thank you very much for listening, and I'm looking forward to the question and answer session. Thanks, goodbye.